Hello dear students, in this session we will discuss about significance of poles and zeros. In the previous class we have studied about the poles and zeros. Pole means the value of denominator polynomial when the function will get the infinity value, and zero means the roots of numerator polynomial when the function will got the value 0. So poles and zeros are critical frequencies. At pole, the network function become infinity, and at zeros, the network function become 0. We have studied about network functions and also about transfer impedance, driving point impedance, and like that. So in that those quantities will be in the polynomial form, that is in the form of a by b. So numerator and denominator will be polynomial, and poles are the roots of the denominator polynomial and zeros are the roots of the numerator polynomial. So we can check the significance of poles and zeros in the case of driving point impedance. If we are considering the driving point impedance, that is Z of S, that is impedance. Impedance means voltage divided by current. So Z of S is equal to V of S divided by I of S. So you can see that a pole of Z of S means that the roots of I of S, right? When the pole of Z of S implies that it is the root of I of S. That means when a pole occur at a particular value of S, the value of I of S becomes 0. That is, a pole of Z of S implies 0 current for a finite voltage, which means open circuit. That means when pole means the value of S in the function I of S, such that I of S become at the particular value of S, the Z of S function become infinity for the pole value. That means I of S becomes 0. So when I of S, that is current, becomes 0 means that it represents an open circuit. So similarly, a 0 of Z of S implies that 0 of Z of S means Z of S becomes 0 when V of S becomes 0. That is, voltage is equal to 0. When voltage is 0 means that it represents a short circuit. That is, voltage across, if the terminal voltage or voltage across any terminals is equal to 0 means it represents the short circuit. So a pole of Z of S implies 0 current for a finite voltage. That means it is an open circuit, and 0 of Z of S implies that 0 voltage or no voltage for a finite current, or that represents a short circuit. So when current equal to 0, that means it is an open circuit. When voltage equal to 0 means that it represents a short circuit. So let us see the significance of poles and zero in the case of driving point admittance. Driving point admittance means that admittance means voltage, current divided by voltage. So Y of S is equal to I of S divided by V of S. So in this case, if pole of I of S implies that V of S becomes 0, that is, voltage becomes 0. That when voltage becomes 0 means that it represents a short circuit. A 0 of I of S means that I of S becomes 0. When current is 0 means that it represents an open circuit. So that is the significance of poles and zeros. It indirectly points to the short circuit or open circuit in the case of driving point impedance and driving point admittance. Next we can see different voltage. These are the transform impedance forms in the case of a network. And next we will find the significance of poles and zeros in the case of a voltage transform ratio. Voltage transform ratio, here we are checking only one voltage transform ratio, that is G21 of S. That is G21 of S means that V2 of S by V1 of S. That means if it is a two-port network, then the voltage at the second port V2 of S divided by voltage of first port gives the voltage transform ratio. So in this equation we can write V2 of S is equal to, that is, voltage at the port 2 equal to G21 of S into V1 of S. So G21 of S and V1 of S are polynomials. We can write in the form of sigma I is equal to 1 to n A by S minus AI plus sigma j equal to 1 to m A by S minus AJ. Here n and m are the number of poles and number of zeros, and G21 of S and V1 of S are the voltage transform ratio. G21 of S is voltage transform ratio, and V1 of S is V1 of S is voltage in the port 1. Here AI and there is a term AI and AJ, and that represents the complex frequencies corresponding to free oscillations, and that depends upon the network function G21 of S. And here the AJ is another frequency that represents the AJ means frequency means that it is a pole value, while frequency AJ constitute the complex frequencies corresponding to the forced oscillations, and that depends upon the voltage value V1 of S. So in this case these are the poles AI and AJ, and that in this case the poles determines the time variation of the response, and zeros determines the magnitude response. So when we are considering other network functions, such as here you know that there are different network functions, such as here we are discussed about voltage transfer ratio. There are other network functions such as current transfer ratio, transfer impedance, transfer admittance, and in all these cases the significance of poles and zeros are similar in the above discussed cases. So let us go to the properties of the driving point functions. So first of all, driving point function is driving point function is the ratio of two polynomials. That means driving point function, there are different driving point functions such as driving point impedance, driving point admittance. In the case of two-port network also there are different driving point functions. So we will go to the properties of the driving point functions. So we can say that it is the ratio of polynomials in S, and polynomials are obtained from the transform impedance of the elements and their combinations. Let these polynomials, let the driving point function is in the form of P of S by Q of S. Suppose it will be N of S is equal to P of S by Q of S form, and here P of S is one polynomial and Q of S is another polynomial. So we can write it in the form of A0 S raised to N plus A1 S raised to N minus 1 plus etc. up to An An minus 1 S plus An. So if we have a network, we can find an equation for this driving point function. So when we are writing the equation for the driving point function for a network containing resistor, capacitor and inductor, we will get the form in the form we will get an equation in the form of P of S by Q of S. So in that P of S will be in the form of this one, and Q of S will be in this form. So we can write this numerator and denominator in the form of P of S is equal to S minus Z1, S minus Z2, etc. up to S minus Zn. Similarly, Q of S can be written in the form of S minus P1, S minus P2, etc. up to S minus Pm. So this driving point function will be in the form of P of S by Q of S. And in this case, the quantities Z1, Z2, etc. up to Zn are called the zeros of driving point function N of S. And P1, P2, etc. up to Pm are called the poles of N of S. So that means when at the zeros, the value of N of S becomes 0. At poles, the value of N of S, that is N of P1, N of P2, etc. will become infinity. So if the zeros and poles are not repeated, then the poles and zeros are said to be distinct or simple. If zeros and poles are said to be multiplicative, that means S minus Z occurs more than one time. That means S minus Z all raised to R is a factor. In such cases, the poles and zeros is said to be multiplicity. That means a pole or zero occur more than once. So a function N of S is said to have a pole or zero at infinity if the function N of 1 minus S has a pole of 0 at S is equal to 0. So next property is that N of S is a driving point impedance. Then Z of S is equal to we know that Z of S is impedance, that is V of S by I of S. And here S0 of N of S is a suppose this is a driving point function, then the 0 of N of S means that 0 of V of S. 0 of V of S means that it indicates that voltage is 0, means it indicates a short circuit. Similarly, a pole of Z of S means that 0 of I of S, that means current will be equal to 0. That means it represents an open circuit. Okay. So next case, if you are considering the driving point admittance as a network function, if I of S by I of S by V of S, in the similar case, if a pole 0 of I of S means that 0 of I of S, that means the current becomes 0, that means the circuit is in open condition. and pole of I of s means that 0 of v of s. In that condition, when voltage becomes 0, that represents a short circuit. So third property of the driving point function is that since all the elements in the circuit are real positive quantities, the coefficients a0, a1, a2, etc. up to an and b0, b1, etc. up to bm are real and positive. Therefore, any zeros or poles, if complex, must occur in conjugate pairs. So this is an important property. We will have a network function in the form of v of s by q of s. That means it is in this form. See, this is in this form. Network function will be in this form. In this case, the coefficients a0, a1, etc. up to an and b0, bn, etc. up to bm are said to be positive and real. That is a property, and therefore any zero or poles, if it is complex, they will occur in complex conjugate pairs. And fourth property is that the real part of all zeros and poles must be negative or zero. So it is a necessary condition for the system to be stable. So if we are giving the network condition, then you should ensure that the real part of zeros and poles must be negative or zero. So then only the system will become zero. Next, fifth property is that the poles and zeros lying on the j omega axis must be simple. Otherwise the function become unstable. And sixth property, the degree of the numerator polynomial p of s and degree of the denominator polynomial q of s may differ by 0 or 1 only. Actually, degree means that it is the highest power of s occurring in the equation. So the degree of p of s and q of s may differ by 0 or 1. And the lowest degree term in the p of s and q of s may differ in degree by 0 or 1 only. Next property, p of s and q of s cannot have missing terms unless all even or all odd degree terms are absent. So this is the properties of the driving point function. Next we will go to the properties of the transfer function. Transfer function means you know that there will be voltage transfer function that is represented by G21 of S or G12 of S, that is representing the ratio of different voltages, that is V2 of S by V1 of S or V1 of S by V2 of S. Similarly, there are current transfer functions such as which is represented by alpha of S. That may be giving the ratio of different currents in the port 1 and port 2, that is I1 of S by I2 of S or I2 of S by I1 of S. Similarly, there are transfer impedance and transfer admittance. These are the transfer functions. So next we will go to the properties of those transfer functions. First property is that a transfer function is the ratio of the polynomial in S, right? That is a right thing, because we know that transfer function is the ratio of, if we are considering the voltage transfer function, it is the ratio of voltage V2 of S by V1 of S. So these all are functions of S. And second property is that coefficients of P of S, the numerator polynomial, and of Q of S, the denominator polynomial, must be real. So the coefficients of numerator polynomial and denominator polynomial should be real, and therefore all the poles and zeros, if complex, must occur in conjugate pairs. That is similar in the case of the driving point functions. This property is also appear for the driving point function. Next, third case is that the real part of all poles must be negative and any pole on the j omega axis must be simple. As in the case of driving point function, this follows from the stability consideration. See, when we are considering the P of S function, when we are considering the transfer function, the denominator polynomial will give the poles. So in that pole, the real part of the poles must be negative. And any pole on the j omega axis, suppose if there is any pole appear on the j omega axis, it should be simple. In such cases, in the case of driving point function also, this condition is should be satisfied, and so it is a necessary condition for the stability. That means for the stability, the pole should lie on the left half of the S plane. That is that it indicates, because real part must be negative, means that the pole should lie on the left half of the S plane. Since poles of the transfer functions are zeros of Q of S, it follows that zeros of Q of S must lie in the negative half S plane. Any zero lying on the j omega axis must be simple. So this is another condition for stability. That means poles of the transfer function means that see, transfer function is in the form of P of S divided by Q of S. So Q of S is the denominator polynomial. So poles of this transfer function means that it is a value of S corresponding to Q of S polynomial. So at a particular value of pole, Q of S will become 0. That means that the zeros of Q of S must lie in the negative half of the S plane, and if there is any complex conjugate zeros, that means it should also lie on the j omega axis, and that should be simple one. So this is a major condition for, this is an important condition for the stability. So poles and zeros must lie on the left half of the S plane. Fifth property is that for G of S and alpha of S, G of S means that it is a voltage transfer ratio, that is voltage V2 of S by V1 of S is a voltage transfer ratio. Similarly, alpha of S is the current transfer ratio, that is I1 of S by I2 of S or I2 of S by I1 of S. That is for a voltage transfer ratio and a current transfer ratio, the degree of the numerator polynomial P of S is less than or equal to the degree of the denominator polynomial Q of S. So if you are taking V2 of S by V1 of S, degree of V2 of S should be less than or equal to the degree of V1 of S. Next property is that the degree of the numerator polynomial of Z2 1 of S and Y2 1 of S. That means Z2 1 of S and Y2 1 of S means that transfer impedance and transfer admittance. That is Z2 1 of S means that V2 of S divided by I1 of S. Similarly, Y2 1 of S is equal to current divided by voltage, that is, since it is Y2 1 of S, that is that will be equal to I2 of S by V1 of S, that we have studied in the previous video. So the degree of the numerator polynomial Z2 1 of S is less than or equal to the degree of the denominator polynomial plus 1. So if you are considering transfer impedance and transfer admittance, it should have a numerator polynomial and denominator polynomial. The degree of the numerator polynomial of this transfer functions should be less than or equal to the degree of the denominator polynomial plus 1. So these are the properties of the transfer functions. And next we will go to the necessary condition for a driving point function. It will be helpful for doing the problems. So the restrictions on poles and zero locations in the driving point functions with the common factors in P of S and Q of S cancelled out. See, we have a driving point function and in the form of V of S by Q of S. Suppose if there is another common terms occur in that function, then we can cancel it out, and finally we will get a form of V of S by Q of S. So in that form, it should follow this necessary conditions. That means first condition is that the coefficients in the polynomial P of S and Q of S of the network function, that is N of S is equal to P of S by Q of S, must be real and positive. So P of S and Q of S coefficients should be positive and real. Next is complex or imaginary poles and zeros must occur in conjugate pairs. That means if there is a pole in the form of A plus IB, then there should be a pole in the form of A minus IB. That means complex or imaginary poles and zeros must occur in conjugate pairs. That means if there is A plus IB is a pole, if A plus IB is a value of S, then there should be A minus IB. Third is the real part of all poles and zeros must be 0 or negative. If the real part is 0, then the pole and zero must be simple. So real part of the poles or zeros may be 0 or negative values, because it is a condition for stability. That means the poles or zero should lie on the left half of the S plane. That means left half of, when it is on the left half of the S plane, that means its real part value will be negative. So the real part of all the poles or zeros must be 0 or negative, and if the real part is 0, then the pole and zero must be simple. Next condition is that the polynomial P of S and Q of S may not have any missing terms between the highest and lowest degree unless all even or all odd terms are missing. Fifth condition is that the degree of P of S and Q of S may differ by 0 or 1 only. Sixth condition is the lowest degree in P of S and Q of S may differ in degree by at most 1. So this is the necessary condition. Actually, this is the conditions that we have discussed in the properties, but it is given in a short means for your understanding. Next is the necessary condition for transfer function. The restrictions on pole and zero locations in transfer functions with the common factors in P of s and Q of s will cancel out, and then you will get a form like P of s by Q of s. And in that form, first property necessary condition is that the coefficients in the polynomial P of s and Q of s of n of s is equal to P of s by Q of s must be real. In the previous case it was real and negative. In this case it is must be real. The coefficients in Q of s must be positive, but some of the coefficients in P of s may be negative. Second condition, the complex or imaginary poles and zeros must occur in conjugate pairs. The real part of poles must be negative or 0. If the real part is 0, then the pole must be symbol. The polynomial Q of s may not have any missing terms between the highest and the lowest unless all the even and odd terms are missing. The polynomial P of s may be missing terms between the lowest and highest degree, and the degree of P of s may be as small as 0 and it will be independent of Q of s. For the voltage transfer ratio and the current transfer ratio means it is the ratio of different currents such as I1 of s by I2 of s. Voltage transfer ratio means that it is the ratio of voltages V2 of s by V1 of s or V1 of s by V2 of s. That means for the voltage transfer ratio and current transfer ratio, the maximum degree of P of s must equal to degree of Q of s. Similarly, for transfer impedance or transfer admittance, that means it is the ratio of voltages and currents. The maximum degree of P of s must equal to the degree of Q of s plus 1. So these are the necessary conditions for the transfer function. So that's all about this topic. Thank you.